Hi, welcome back. In this lecture, we're going to look at more in detail at a cache memory subsystem and how the performance of the cache memory subsystem impacts the overall performance of our application. We saw in the previous lecture that we have three main memories in our computer system. There's the main memory that contains all the program data. There are cache memory that are very fast but contains only a copy of the memory data. And then there are registers that are super fast and contain only working data. We also seen in the previous lecture that loads and stores, and in general all the memory operation, can be as important as computing, as important as floating point operation. Simple models that look at sustained memory bandwidth, still ignoring details of the cache effects, can still provide a very useful bounds on the performance of our application. This was particularly true for our example of sparse matrix multiply in the previous lectures, and is in general true for all the problems where the majority of the data accesses are consecutive. So note that we provide a bound, a guaranteed not to exceed value for the performance. So this was a maximum value for the performance that can be achieved. So let's look at more in detail of the cache memory system. Because of the way caches are implemented in the hardware, there are trade-offs between the size of the cache, that is the number of bytes that the cache can contain. This is also called capacity. There is a trade-off on the speed. There is a trade-off on the power. So L1 is the fastest cache, but is typically the smallest one. And also there are two other, at least one or two other caches, L1, L3, where L3 is also called LLC, last level cache. They provide an intermediate performance / size trade-off. Different kind of memory, they also provide a different number and different speed to access. So this table presents typical access time for cache-based system. To access of L1 cache, L1 is very fast, so it only take a few clock cycle to access L1 cache. L2 cache is larger, so it has a larger capacity, but also slower. Typically, L2 cache has an access time of the order of 10 cycles, so between 3 and 10 times lower than L1 cache. How much time it takes to go to the memory or to the RAM? Typically, 200 clock cycle. That is roughly 100 times slower than accessing L1 cache. So here is also you understand the importance of using cache properly. You can just using L1 caches, you can speed up by 100 times the data access. In the last part of this course, we also are going to look at how to access memory out of the node. So this is called remote memory. So this is typically around 2,500 to 5,000 cycle, depending on how good is your network. So this is a factor of 1,000 lower than accessing L cache, and is typically between 10 and 20, if not more sometimes, the time that takes to go to the local memory on the node. So what is the impact of memory hierarchy? So we on the impact of memory hierarchy on our performance application. So here we run the stream benchmark to obtain different values of the bandwidths. On the x-axis, we have the data size in bytes. So we are basically streaming arrays of different size. And for each side, we measure the bandwidth. The bandwidth in this plot is in the y-axis and is calculated in megabyte per second. So the red dot here are the value that we have been measuring, and then the lines are basically putting all together. We can recognize some pattern in this plot. So this pattern, this structure is due because of the memory hierarchy. For small data size in this region here, the data fits to the L1 cache, and the L1 cache has a high bandwidth. For intermediate values, the data fits into L2 cache. So you see that the, the bandwidth is still comparably high, but lower than the L1 bandwidth. And then for a rather large array size, you will see that the data is not fitting into L2 or nor L1, but only on the main memory. So the data need to be loaded from main memory all the time, and the bandwidth is therefore is slower. So looking at this number and looking at how the cache memory subsystem looks like, we can go back to our original performance model for the sparse matrix vector multiply. So we come up with a simple execution time that is as this form, but we also now can add a term that is the fact that to access the cache time takes some time, and to load the data to the cache takes some more time. So to take in account the cache performance, we introduce one more factor that is RC, that is the time to read from the cache, right? So we add it here to read X from the cache. Note also that we need to include the time from to read into the cache from the memory. So we still have we're still paying the cost of accessing the main memory. So we are adding here one more term. This was 0.5. We add one load of a double precision element from the memory to the cache. So so one important point when looking at the caches is that the data in caches is not loaded byte by byte, but is loaded and stored also in chunks. So most of the communication in a computer is carried out in chunks. There are actually blocks of bytes of data that move together. So we have these chunks of data all moving together. So in the memory hierarchy, data moves from between memory and caches and between different levels of caches. And when we look at the data movement between caches and between caches and memory and main memory, these blocks are called cache line. So let's include the impact of the cache lines on our performance modeling. So the data is moved between different levels of the memory in group of words called cache lines. Cache lines are typically between 64 to 128 bytes long. That is also 8 to the 16 double precision words. An important point to realize is that even if we don't use the data is moved and occupies in space in the cache. So if we have the wrong data in the cache, this is particularly bad in the sense that we are not going to use it, but just wasted the cache. Another important point that I want to make is that most of the programming languages they don't provide any means to program explicitly caches. So this performance feature is not captured in most of the programming languages. When looking at the data is important to understand the concepts of locality. We have a different kind of locality when talking about caches. We have temporal locality that is basically reused the same data. So we have some data in the cache that can be is accessed in time many times. And this was our assumption in the sparse matrix case for the usage of X, where the X data is reused all the time. So we don't pay the time to access the main memory. Together with the temporal locality, we also have a spatial locality, that is the reuse of the nearby data. So for instance, if we have an array and we are accessing one element of that array, it's very likely that all the um, array elements that are consecutive to the array element that we are accessing will be also loaded to the cache, right? So if we are accessing this nearby data in the array, it's very likely that we're going to reuse the cache. So this kind of locality is called spatial locality, right? And this match the hardware in the sense that how much data you can bring to the cache. This depends on the cache capacity, right? And this is hardware feature. Alpern and Carter, two computer scientists, suggesting a different breakdown based on the algorithms. So an algorithm can be local when the data has both temporal and spatial locality. It can be semi-local when the data has only spatial locality. And it can be non-local when data has neither spatial nor temporal locality. So we can go back to our performance model. So we now understand that achievable memory bandwidth strongly depends on small, fast cache memory. The temporal locality reduces the need for sustained memory bandwidth since the data is going to be present in the faster memory. So we saw in the matrix multiply example that the data for X was residing in cache. We basically didn't consider the cost of loading X from the main memory. So all this very simple performance modeling based on temporal and spatial locality leads to an important rule of thumb when doing performance modeling. So the few things we need to do is to identify dominant terms when it comes to our expression of a performance model. So for instance, we saw that we could neglect part of the execution time because certain operations were completing only n row times instead of being n z times in the case of the sparse matrix multiply. We also understand that architecture are way too complex for any other approach that do not try to at least simplify. And so we rely on simple mathematical modeling to predict or at least provide a maximum peak performance for our application. We will see, and it's particularly true that simple model like does it fit in the cache are actually quite good in predicting performance. So this does it fit in the cache model assumes that all the cache is actually available. This is not typically true. We will see later on how to refine this model. And also this model assumes that for multiple cache levels, we can use the performance of the smallest but also fastest cache in which the data fits. How do we go from measurement to the model? On the left side of the slide, so we have a measurement from a stream. We go to the model, basically assuming that the bandwidth for a given size of our array is fixed, but still recognize that there are different caches size that have also different memory bandwidth. Let's look at more in detail at spatial locality. So non-consecutive memory accesses. So for instance, we have an array that is accessed in stride. So these non-consecutive memory accesses expose more details about the memory structure, how the memory in hardware is actually implemented. So the effective cache size reduces reduced when not all the data on the same cache line is actually used. It's important to have spatial locality in our algorithm. Um, and spatial locality is particularly important to get full use of the cache line uh, size. So we can use this extra information for our performance model, and we can use the fact that cache line size can help us in refining performance bounds. In particular, we saw that if we are not able to use all the cache line, this reduces the effective cache size to the same fraction of the utilization of the cache. So for instance, if we have one 8-byte value used from one 28-byte cache line, or one of the 16 of the line, the effective cache size is only 1/16 of the full size, because we are not going to use the rest of the data that has been loaded on the cache line, therefore wasting the space of the cache line. So let's put everything together. This is one of your assignment. We are going to look at spatial and temporal locality when at your particular processor with a particular cache system. The way to do that is to prepare a so-called memory mountain, that is a two-dimensional function of the read bandwidth versus temporal and spatial locality. So here on the right we have a plot of our memory mountain. On the z-axis we have the bandwidth as a read rate. On the y-axis we have the size of the array that we are operating on. So very much like on the stream example. And the y-axis, we have the stride where our array is assessed, right? So we will have, if the stride is 1, our array is assessed consecutively. If we have a stride that is not equal to 1, we will jump different parts of the array. So this is going to be one of your assignments. So you will look at more in detail at this. This was the last slides. In the next lecture, we're going to look at how to measure application in HPC system. Talk to you soon.